Hello, in this video we shall be discussing about the multiplication of vectors in the series vectors motion in a plane. So multiplication of vectors is not just any multiplication like the way we do in the case of just numbers where we are multiplying one number with the other. That means we are trying to find the number of times one number is getting multiplied or is getting added, uh, number of times a specific number is getting added. Suppose I say 5 times of 2, that means 5 is getting added twice, so I'm considering 5 two times. That means 5 and 5. Obviously we are adding them, so 5 plus 5 is 10. This is the way multiplication goes. You know all of that. But in case of vectors, with them possessing another thing other than the just the magnitude, that is direction, we need specific rules for multiplying them. Two vectors can be multiplied to give a scalar quantity, and that is known as the scalar product of a vector multiplication, where two vectors multiply to give a scalar. Two vectors multiply to give a scalar. Now, how is that possible? We'll be knowing them in a very short time from now. And the next obviously is the vector product, where the result is a vector quantity. Two vectors multiply to give a vector instead of a scalar. So when we have the result as a vector quantity, we call it the vector product, and the result as a scalar quantity, we call it the scalar product of two vectors. So let's now start off with the scalar product. Now the scalar product of two vectors is just, all I can say is the projection of one vector over the other, or the multiplication of the projection of one vector over the other. If we have two vectors A and B, so this is the vector A while the other vector is B, and they are having a certain angle theta with respect to one another, then we define the scalar product of A and B by the symbol dot. So this is A, read as A dot B. So A dot B is the scalar product of A and B, where we have the result as the magnitude of A multiplied with the magnitude of B multiplied with the cosine of the angle separating them, in this case being theta. So AB cos theta is the uh, dot product, or the result of the dot product of two vectors. Now, as you can see, I haven't written any kind of, or I haven't given any kind of specific direction to the product, because this is a scalar quantity. Why so? Because it does not have a specific direction. And why is that? Let's see for ourselves. If we consider these two set of vectors that I have drawn over there, then I can say that I can drop a perpendicular from A over B. Now this entire thing is a B that I have drawn or marked with the curls, and this amount of thing that is up to the perpendicular, this is the perpendicular that has been dropped, that has a value A cos theta. If you have gone through the components of vectors that I had that I discussed in the previous video, just the previous video on vectors, then you can obviously know what I'm talking about. So this is a cos theta, and that is obtained by dropping a perpendicular of from the vector A over the vector B. Now multiplying those two things, what does that give? So we have a cos theta along the direction of B. This is along the direction of B. So a cos theta multiplied with the magnitude of B, what we have is a B cos theta, which is what we have mentioned over here. Now consider the other way around, where I am dropping a perpendicular from B on A. Let me just specify it with some other color for your better understanding. I am dropping a perpendicular from B on A. This perpendicular dropped over A, obviously you have the same angle theta, and so this curl part that I have just marked with red is B cos theta, just the other way around, while this entire thing is the A vector, right? And so what we have is along the direction of A, along the direction of A, what we have is we have A multiplied to B cos theta. If we are multiplying both of those terms or both of those vectors that we have achieved, the magnitude of them, then we end up with the same thing, that is AB cos theta. So now as we are multiplying both of them, be it in the direction of A or be it in the direction of B, we are obtaining the same result as I am encircling right now. The same result with no specific direction, or no defined direction. And as a result of that, we end up with a scalar quantity which has a magnitude but no specific direction, and because of that only we can say that this is a scalar product of two vectors. Now this dot product is also popularly called as the dot product, that I'm just writing over there in brackets at the top. Dot product of vectors or scalar product of vectors has some certain properties, of course. So the properties in this case being, the first one being that it's obviously dependent on the angle. The angles with the variation in angles, you can get specific values for 0 degrees, that is both the vectors lying along the same direction, the angle being 0. You have A dot B is equal to AB cos 0, which is just equal to AB. While it becomes negative for theta is equal to 0 degree, you have A dot B to be equal to AB cos 0, which gives me cos 0 is obviously equal to 1, cosine of 0 is 1, so which gives me AB. For theta being equal to 180 degrees, you have AB cos 180, so cosine of 180 is minus 1, and so you have a minus AB, which is a negative. And this value goes to 0 for angle between them being 90 degrees, because you cannot have any projection of a vector on any axis which is at right angles to it. So AB cosine of 90 degrees goes to 0, so this entire thing goes to 0. So these are certain specific values that you can have, while in case of the order of the multiplication, that is a dot b is giving us ab cos theta, which is obviously the same when we take b dot a, which is ba cos theta, and makes no difference whatsoever, which means that this is commutative in nature, or it obeys the law of commutation. Then that means you can commute one vector to one side and the other to the other. It also obeys the distributive law, where you have a certain vector c to be dot product with a, the addition of a and b. So you have c dot a, or a dot c you can say, because of the commutative law, plus c dot b or b dot c, whatever it may be, both are being the same. So this is the distributive property of vector multiplication, distributive property. While also in case of vector being multiplied with itself, now if I have a vector a which is being dot product with itself, obviously you have the angle between the two a's or the a vectors to be 0. So you have a times of a times of cos of 0. Cos of 0 goes to 1, you know that, so it is simply a squared. So a dot a is a squared. But as you know that in case of perpendicular values, or in case of 180 degrees, the values are different, being 0 and minus respectively. Now we had already discussed about the unit vectors. The unit vectors in three-dimensional space along the x, y and z axis. So this having unit value that I have drawn for the coordinates over there. The unit values along the x direction is I cap, while along the j direction or y direction is j cap. Along the z direction is simply k cap. So these are the unit vectors along the directions that have been provided. And if I am to multiply the unit vectors, so I cap dot with I cap with the directions being the same, the magnitude of the unit vectors is obviously unity, that means 1. So 1 multiplied with 1 multiplied with cos 0, you end up, which is also equal to 1, you end up with 1. So I dot I is equal to j dot j cap, plus, which is also equal to k dot k cap, which is obviously equal to 1. But if we multiply them between themselves, or with respect to the other term, just like I cap dot j cap, then I has the value or magnitude of 1, j has the magnitude of 1, but the angle between them, because these are coordinates, these are the Cartesian coordinates, so the angle between them is 90 degrees, and cosine of 90, as you know, is 0. So the value goes to 0, and not just in case of I cap dot j cap, it is also in case of I cap dot k cap, or even j cap dot k cap. We can take it the other way around, j cap dot I cap, k cap dot I cap, k cap dot j cap. It's all the same because of the commutative property of vector multiplication, scalar product. So these are the multiplications that are involved in case of the unit vectors. Now if I am to consider the arrangement of a particular vector uh, in terms of the three-dimensional coordinates that are available, just like the case of, let's take the example where we have a vector a which is equal to a1 I cap plus a2 j cap plus a3 k cap. We have discussed these kind of representations already in the previous video. You can go through them if you want to. B vector, let that be any other vector where you have a B1 I cap plus a B2 j cap plus B3 k cap. So these are the two vectors, and suppose we want to multiply them. Now multiplying these two vectors, A dot B is giving us the entire term, that is A1 I cap plus A2 j cap plus A3 k cap, dot with B1 I cap plus B2 j cap plus B3 k cap, bracketed. Now this term that you are going to multiply is going to give you, you know that I cap dot I cap will be equal to 1 I cap dot j cap, or I cap dot k cap is going to be 0. So all we are going to have over here is that A1 B1 I cap dot I cap, which goes to 1 obviously. We'll take the ones later. I need not multiply the first term in the first bracket, that is A1, with B2, because I know that I cap dot j cap goes to 0. So only I cap multiplied with I cap terms in case of dot product. J caps get multiplied with J caps in case of dot product, and K caps get multiplied with K caps. The resulting obviously vector is value is obviously equal to 1 with these dot products involved. So all I have is A2 B2 plus A3 B3 for the rest of the multiplications that are available there. So this is the value of dot product of two vectors represented in three-dimensional space. As obviously you know that A dot B, as discussed earlier, is simply the magnitude of A, the magnitude of B, multiplied with cosine times of the angle between A and B. And in that case, what we have over here is that, as you know, you have A dot B to be equal to A1 B1 A2 B2 plus A3 B3. So we can just put those values over here to just get the value of theta maybe. So A1 B1 plus A2 B2 plus A3 B3, which is what we have obtained for A dot B. And on the right hand side, the magnitude of A, as you know, as we've discussed earlier, is just the square root of A1 square plus A2 square plus A3 square, and the magnitude of B is obviously B1 square plus B2 square plus B3 square, all under root multiplied with cos theta. So this being the magnitude, what you have for the value of cos theta to be equal to A1 B1 plus A2 B2 plus A3 B3 whole divided by root over of A1 squared plus A2 squared plus A3 squared multiplied with the square root of B1 square plus B2 square plus B3 square. This is the expression that you can use to obtain the value of the cosine of the angle between the two vectors, and from that you can obtain the value of the angle as well, taking the anti-cosine or the inverse cosine as we call it. Now, with the dot product and the unit vectors involved in dot product sorted, we can move over to the vector product of two vectors. Now in case of vector product, as the name suggests, we end up with a vector quantity, means it has a certain direction. Okay, let's start off with that. Vector product, also known as the cross product, because it is represented by cross, that is the multiplication sign, but here it is specifically termed as cross instead of multiplication. So let's say C is the product vector of the cross product or the vector product of two vectors, that is A cross B. Now, if I consider the vectors A and B, this is a plane that I've drawn over there, and I have a vector A and a vector B. As shown in the figure over there, A and B lie on the plane. Let the plane be plane S, lie on plane S, right? And the product of these two vectors will be normal. That is, the vector C that I am considering is normal to the plane. C is normal, or I can say perpendicular. Normal means perpendicular to the plane S. Now it can be perpendicular in the upward direction as I have shown over here. It can be perpendicular in the downward direction, but it depends on which vector I'm taking first or considering first. Now, how do we do that? We consider the now let's just discuss the magnitude of it. C is equal to A, the magnitude of A, multiplied with the magnitude of B, sine of the angle between A and B, whatever may be the angle theta between A and B, sine of that angle, and here we have n cap, where n cap is the arbitrary direction of the product vector, that is C. N cap in this case is directed outwardly, as I have just represented right now over there in that figure. This is n cap, which is directed out of the plane as per my diagram, as per the product, as per the order of the product that I have considered. Now, what do you mean by the order of the product? I am considering the vector A first to be crossed with the vector B. On the other way, if I was to consider the vector B first and cross it or take the cross product with A, then this will give me a different result. Different in terms of, the difference comes in terms of direction, not in magnitude. The magnitude remains the same. That is, you can write A first, then B next, or B first, A next. That doesn't matter as far as the magnitude is concerned, because it's going to end up multiplying the same thing. But the direction will be exactly opposite to that of n cap, which is represented by the minus sign over there. That means it will be acting in the downward direction as per the figure that I have shown. Let this be some other vector. Let us say this is D vector. So the D vector in this case will be directed right there in the downward direction. This is D vector. So the D vector is B cross A, which is exactly the opposite of C vector. Now, how do we know the direction involved? The rule for obtaining the direction is known as the right hand thumb rule. Let's get into that rule first. Now, all you can do is consider the right hand, your right hand. The right hand has 5 fingers, and those 5 fingers you extend. Let me try and explain this to you by drawing that. I won't be, or maybe or may not be, I don't know if I can draw the hand, but definitely I can give you an idea. I'll try that. So this is a vector. This is another vector. They lie on this plane. Right. What you do is, your right hand These are your fingers, obviously. Right. All you have to do is you face your palm from the first vector. Let us say this is A, the first vector, and B is the next vector that you wish to take the product. So from A crossed with B. So all I have to do is face the palm of the right hand from the first vector. Here the first vector is A, to the second vector, which is B in this case. All right, you are now having the face of your palm from the A towards B, and curl the four fingers extended. You have extended your palm, the four fingers are pointing towards A. You curl them from the sense A to the B. Curl the four fingers extended from first vector to the second. And in the process, extend your thumb of the right hand. And the extension of the thumb gives, that's not a good thumb though, but the extension of the thumb here gives the result, or the gives the direction of the product. This is what you have as the right hand thumb rule. There can be many more versions of this. Right hand screw rule, or the bottle cap rule, but always the right hand bottle cap rule. Now all these rules are the same, obviously, because in case where you are twisting the screw, or you are twisting the cap of a bottle, when you are closing the cap or you want to cap the bottle, you just rotate it in the clockwise sense. In obviously the right hand, it rotates the bottle in the clockwise sense, the cap of the bottle in the clockwise sense to close the bottle. That means the cap is going downward or into the mouth of the bottle. It is getting stuck to the mouth of the bottle. Whereas when you try to unbottle it, that means you try to rotate it in the counterclockwise sense, it comes out. So likewise, consider consider your palm, the palm to be directed while you are closing the cap of the bottle, or you are screwing a bolt, right? You're screwing something, you're using a pile driver to screw a bolt into the whatever surface, wooden surface that you want, and you are just screwing it in. As you are twisting, you twist it for inward motion of the screw, you twist it in the clockwise sense, and for the outward motion you twist it in the counterclockwise sense, and as a result of that you have the direction of motion of the screw, or the direction of motion of the cap of the bottle. In this case, the figure that I have drawn over there, the thumb extended is giving the direction of the product vector, as I curl the four fingers of the right hand from the first vector to the second vector. Now consider the case where where the where I'm rotating the fingers from B towards A. Obviously the palm now faces from B towards A. So you have your little finger first, then the ring finger, then the middle finger, the central finger, and the forefinger, all directed. These are the your palm that is facing in this direction, and the thumb now faces downward, is directed downward as you curl from B to A. Curl the four fingers of your right hand from B to A, and as a result of that, what you have is B cross A points downward to the plane containing A and B. So one thing is for sure in this case is that whenever you have the product, the vector product of two vectors, the result or the product of two vectors in cross product, the product of the two vectors in cross product is always directed normal to the plane containing the vectors. Normal to the plane containing the vectors, either it is normally outward or normally inward. Now in case of the plane of the paper that we are using, or this plane of the paper that you're viewing on screen, if those two vectors lie on that plane, then you have the A vector over here, B vector over here, separated by an angle theta. So as I use the right hand thumb rule or the screw rule, if I am to rotate the screw from the first vector A to the next vector B in terms of the order that I have just written over there, A cross B rather than B cross A. So in case of A cross B, what I'll be getting is that the product vector C is going to be directed into the plane of the paper that we are seeing on screen right now, because when you are rotating you are obviously rotating the screw in the clockwise sense from the first vector to the second vector. The first vector over here is A, which is at the top, not at the top but on that side of the B, and the vector B is below it. So as I use the screw or rotate the screw from the first vector to the second vector, it will be rotated clockwise, and while rotating in the clockwise sense, it is definitely going to drive the screw into the plane of the screen or the paper that you're viewing right now. So in that case, the C vector is directed into the plane, and the into the plane is usually represented by cross encircled. This means into the plane in which the vectors are present, or the plane that we are considering right now. In case of B cross A, what you have is the C vector or the C dash vector, because it is a different vector now with a different direction, although the magnitude being the same. You have the screw coming out of the plane because you are driving the driver anti-clockwise or counterclockwise from B towards A. So from B towards A, B cross A, the screw is coming out of the plane, and it is represented by this dot encircled out of the plane. So this is the basic rule of a vector multiplication of two vectors. We'll be dealing with the properties of a vector multiplication in the next video. We've run out of time for this video. We'll be dealing with the properties of vector product, and then many more the unit vectors and many more things associated with it. But that is for the next video. Till then, thank you for watching.